Okay, well, we have a short day today. We're going to start off with some talks, and then we'll have, after the break, we'll have discussion of the breakout sessions. And I think we have on the schedule kind of perspective from funding agencies and a final discussion and wrap up. I don't think we might have one agency representative here. So I think that's going to be a sort of a strategy session at the end of the morning. And I'll start off by saying I was impressed yesterday with all the modeling work. I mean, it's I guess I'm out of touch, but it just seems like compared to the last time I was in a meeting like this and people talked about models, that the models have just really blossomed in terms of their capabilities and all the detail that they provide. And in our breakout session, I was impressed with hold on a minute, let me shut this off. A couple of the modelers were saying, well, gee, we would love it if there was some better mechanism for sharing data and doing intercomparisons and getting access to this data that we might use to validate the models and perfect things. And I think the observationalists maybe feel kind of the same way, but from the observation side. And it reminded me of the situation with the ENSO. And back in the, I guess it was back in the 60s, people decided we need to understand why we have these El Niños and what's going on there. And it was an atmospheric and ocean process. We knew that. And so the scientists got together and said, well, we need sort of an organized program of analysis and modeling and observations to get at what's going on. And so they joined together and pushed for an observing system. And the Toga Tau array was born, and they really developed a lot of that equipment and mooring technology from a pretty primitive state into something that really now is an operational system. They learned a lot about El Nino to the point where it's part of the common vernacular. I mean, here in Seattle and the Washington area anyway, we hear about El Nino and what the prediction is for the coming year and what's your weather going to be like. Are you going to be skiing here in town, or are you going to be skiing up in the mountains? And but it kind of got going, and the reason that happened was because a bunch of scientists got together and said, we really need to get a coordinated program of observations, modeling, and so forth. And I think that that's something that you all could do. And so I guess I'm just going to ask you to kind of think about that. And then in a couple of hours, when we when we don't have the perspective of the funding agencies, to think about, well, what would you be willing to put into some of a joint effort to go out and ask the agencies to come up with an observing plan that they could fund and a corresponding analysis and modeling program that would all be coordinated so that we get the maximum amount out of the whole effort. Anyway, that's the pitch I wanted to make. And so now I guess we'll turn it over to Mary Louise and her speakers.
Okay, thanks, Jamie. So I guess we're going to get started then. Yeah. Excellent. So our first speaker is Stefanie Semper. Stefanie.
Hey, good morning, everyone, and thanks for having me. I'm Stefanie Semper, and I'm a postdoc at WHOI Oceanographic Institution and the University of Bergen in Norway, and I'm funded by a Marie Curie Fellowship of the European Union. So today I want to talk about formation and circulation of dense water from a 2-year moored record in the northwestern Iceland Sea. And so I'm talking about the Nordic seas, and I know that you all are a bit more familiar with the Arctic Ocean, so I give a little bit more of an extended introduction about the Nordic seas. But I also want to point out that some of the processes that we are seeing in the Nordic seas right now, I think will become relevant for the Arctic Ocean in the future. So let's get started. Water mass transformation in the Nordic seas is crucial for the climate. So this is really where we have the warm saline Atlantic water inflow crossing the Greenland-Scotland ridge. This water is transformed, cooled, and densifies. It sinks down and is being transported back to the south, crossing the Greenland-Scotland ridge through gaps, and then supplying the lower limb of the Atlantic meridional overturning circulation. And there are pretty much 2 main mechanisms of how overflow water is formed. So overflow water that then crosses the ridge and supplies the lower limb of the AMOC. And I refer to overflow water as everything that's denser than 27.8 kilogram per cubic meter, which is kind of a common limit of overflow water. And one of the main formation mechanisms is transformation in the rim current system. So this means that the warm Atlantic water, as it progresses northward around the Nordic seas and also the Arctic Ocean, is progressively cooled and densifies. And then this water is mainly exported through the overflow at Denmark Strait by the East Greenland current. So the second main mechanism of formation of this overflow water is in the interior basins of the western Nordic seas, so the Greenland Sea and the Iceland Sea. And this is actually where the densest overflow water is formed in the Nordic seas. And this water is then mainly exported by the North Atlantic jet flowing westward toward the Denmark Strait overflow, and by the Iceland Faroe Slope jet that we discovered a few years ago towards the Faroe Bank channel, here flowing eastward along the ridge. So why is this overflow water denser in the interior basins? So this is, first of all, we have weakly stratified water column, but then also we have the ice edge. So this contour shows the 50% sea ice edge from a reference period 1960 to 1990, where the sea ice edge extended into the interior basins. And near the sea ice edge, we have the highest ocean heat fluxes. So cold air that comes from Greenland and over the ice meets the comparatively warm ocean, and then we have a lot of heat loss, which then can kind of deepen the mixed layer. However, as you all know, the sea ice has been retreating, and in the Nordic seas, it has kind of retreated towards the east coast of Greenland. And this, here I'm showing now the last decade, 2010 to 2020, and we can see that large areas of the Greenland and Iceland seas have now become ice-free in winter. And this was really one of the motivations for us to place a mooring here in the northwestern Iceland Sea, because this area has not been accessible before in wintertime, and now we can really see what dense water formation looks like there. Another reason to place the mooring in this area was that this is a gap where, so we still don't know how much about the circulation of these subsurface currents, and somehow this water, the dense water that's formed in the Greenland Sea, has to make it through the Iceland Sea towards the slope north of Iceland, where it then supplies these slope currents. And this mooring is placed in what we call the Egvin offset, which is a gap in the mid-Atlantic ridge that extends north of Iceland. And this gap could be a potential passage for a dense water formed in the Greenland Sea that then makes it from the western Iceland Sea into the central Iceland Sea towards the slope. So yeah, the questions I want to address today are how dense overflow water is formed in Egvin offset, and then what are the processes that affect the mixed layer evolution at the site, and then is this Egvin offset a major passage for dense water exchange between the Greenland and Iceland seas? What can we learn about the circulation in the Nordic seas? Okay, so first of all, I want to introduce the data set. And we have data from a mooring, which is very unique because, first of all, as I said, this is a sparsely sampled region. There was no wintertime access earlier. This is a 2-year-long record from summer 2016 to summer 2018. And it was very well equipped in the vertical. So we had 25 instruments, 21 of them were temperature sensors. And also the temporal resolution was rather high. So most of the instruments measured every 15 minutes. And some of the temperature loggers even every 30 seconds for the course of this 2-year period. The most remarkable thing, though, is that the uppermost instrument was located at 8 meters depth. This was unintentional. We planned it to be at 50 meters depth. It ended up at 8 meters depth, so we are super lucky that we got this mooring back, also because the sea ice passed the mooring in the course of the 2 years. But now, of course, we have this really near-surface record and can really look in the into the air-sea exchange. So here, I'm showing you now the temperature evolution over the course of these 2 years. On the right-hand side, the black triangle shows the locations where we had the temperature sensors. And clearly, you can see the seasonal variability of warm waters near the surface in summer and then cool winters. But it's quite striking how different these 2 winters were. So the first winter, 2016-2017, was very cold, while the second winter, 2017-2018, was much warmer in comparison. And this is reflected also in the mixed layer depth, which reached maximum depth of up to 450 meters in the first winter, while in the second winter, the maximum was 350 meters, but then there's also a lot of variability, and mainly it was actually shallower than that. And this is one of the things today I want to explain why were these 2 winters so different. We can look at this mixed layer evolution now as a time series. So in blue, we see the mixed layer temperature, and in black, the mixed layer depth. And there are 2 stages of what happens during the course of a winter. So this is the first year. And in the beginning, the mixed layer first is cooled. And then at some point, it doesn't really cool any longer, but the temperature stays rather constant. So this is then when we break through the stratification, and then actually we reach this more weakly stratified layer underneath. And then it takes much more to actually cool because we have a much larger layer to cool over. But then it's actually the mixed layer depth that is changing. And textbook-like, it would just deepen during the course of the winter, but then here we have a lot of variability, and this is because of lateral advection at the site. So in between, it's actually shoaling again, and then we are trying to deepen more. So first mainly cooling, then mainly deepening, but this structure is not, or this evolution is not really seen in the second winter. So we start off by cooling the mixed layer, but then during the second stage, we don't really cool any longer, but we also don't reach really these deep mixed layers. And this is what we'll try to explain. So if you look at the properties of the mixed layer in temperature and salinity space, now this is colored by time. So we have the mean and the standard error of the properties. We can see that we start out in October with relatively warm water, and then we cool, it becomes denser, and reaches during winter a density of up to 28.03 kilograms per cubic meter before the mixed layer restratifies in May. And for the second winter, we actually start off with a little bit of fresher water, but we also cool a lot during the first month. But then during the course of the winter, we don't really reach as high densities as in the first winter, also until then we again restratify in May. So the difference between the maximum densities that we reached at the site was 28.03 kilogram per cubic meter in the first winter and 27.97 in the second winter. And maybe you don't really have a handle for this, but this difference is significant, certainly, in what kind of dense water we are forming. And the second thing is that both of these densities are relatively high, so these are dense waters that then can supply the lower limb of the AMOC. And to put this a bit in a perspective, so similar mixed layer densities were found in the central Iceland Sea about 4 decades ago. So then it was no more normal that we had kind of these high densities there. But now the mixed layers formed in the central Iceland Sea are much less dense, and it has kind of shifted towards the west. And this, of course, is related to the retreat of the ice edge. So the densest mixed layers are kind of following the ice edge. So if we look at now, again, the 2 winters and the difference, we started out by looking at the sea ice edge, and here we see a mean map for the winter sea ice edge in the first winter, where the sea ice extended into the interior of the Greenland Sea, and on average, it was about 99 kilometers away from the mooring site. For the second winter, however, the sea ice was much more confined to the East Greenland Shelf, and it was on average about 126 kilometers away. And this difference then also leads to a difference in the turbulent heat fluxes. So as I mentioned before, these cold air outbreaks, this cold air, these storm events that come off the ice edge, they lead to very high heat flux directly near the ice edge. And of course, the closer the ice edge is to the mooring, the more heat fluxes we get at the mooring site. And in addition to just the location of the ice edge and the heat fluxes, also in general, the mean heat fluxes in the first winter were larger in the first than in the second winter. On average, this is like 104 watts per square meter compared to 88 watts per square meter, which may not seem like such a big difference, but then it's also about the distribution of when these heat fluxes occur. So we looked into the distribution of these events, these cold air outbreaks, and you can classify cold air outbreaks according to their strength. So based on the temperature difference between the 800 hectopascal layer and the skin temperature, we divided them into moderate, strong, and very strong events. And in the first winter, we can see that there's a rather even distribution of these events. There were 16 in total, and they led to about 54% of the total wintertime heat loss at the mooring site. So these events are super important for the actual heat loss and evolution of the mixed layer. For the second winter, however, we see that most of the events were concentrated in the first half of winter, while there was hardly anything going on during the second part. And in total, the heat loss due to cold air outbreaks was only about 40%. And this really explains the difference between the 2 winters. So if you go back to this plot where we see that for the first winter, we had this even forcing, we go from the cooling to the deepening phase and reach these really deep mixed layers. We don't have this support of the cold air outbreaks in the second part of the second winter. So this is why advection kind of dominated. We have this shoaling going on, all of this variability, but we don't really get these high heat fluxes that actually led them to the deepening. Okay, so now we want to talk a little bit about the connectivity and this passage of the Egwin offset. So the mooring was placed on the southern side, and based on geostrophy, we would kind of think that we have flow from the western Iceland Sea to the eastern Iceland Sea, and we kind of came up with an area or width for how far this one mooring is representative to actually be able to calculate volume transports. So this was then based on bathymetry and hydrographic surveys that we had. So then we computed how much transport is there of this overflow water in the mixed layer. And of course, overflow water is formed during winter time. And we see there's a lot of variability, and positive transport numbers are now going eastward, so into the central Iceland Sea. But on average, so no matter what width we are kind of using, there is hardly any transport eastward in the mixed layer of everything that's denser than overflow water. So there's not much local production and export of this overflow water. Then we can also look at a deeper layer, and this is now between the isopycnals of 28.04 and 28.06, and this is what we call the North Icelandic jet transport mode water, because this is kind of the densest overflow water that we find at the ridge. So it's kind of interesting to see where does this actually come from and how does it make it to the overflows near Iceland. So in this deeper layer, we actually get a transport between 4 and 8 millisverdrup, so depending on the width again, but this is really not a lot. So this was much less than what we expected. So we can kind of conclude that this passage, the Egwin offset, is really not a highway for kind of this dense water from the western to the central Iceland Sea. So there must be some other gaps in the ridge, maybe in the Jan Mayen Ridge farther to the north, where this dense water actually is passing. However, we also deployed an Argo float near the mooring site in winter, and in the first weeks, it kind of drifted Then it was parked at the mixed layer, drifted around the Egwin offset, but then when it reached the exit of the Egwin offset, we parked it at 1,000 meters depth, and then it nicely followed the bathymetry here at the outskirts of the Iceland Sea gyre. It made it to the west into the spar fracture zone, but then turned east again, and then followed again topographic contours towards the slope of Iceland. And here then, of course, it could either go west in the North Icelandic Dret or east in the Iceland Faroe Slope Dret. But this really shows a pathway and a connection of how actually the northern Iceland Sea may be connected to the southern Iceland Sea. And this is really something that we didn't really have an idea about of how this dense water actually makes it south. So to sum up, we showed that the dense water formation now transitions from the central to the western Iceland Sea, kind of following the ice edge. And now we find denser mixed layers, or as dense mixed layers as we had seen in the Iceland Sea about 4 decades ago. So there's really a transition and a shift. And when we look at these 2 winters that we have data from, we find deeper and denser mixed layers in the first winter. And this was because the mooring was located closer to the ice edge and there were higher mean heat fluxes. So it's all about the colder coming of the ice. So the colder outbreaks, these short storm events, were super important for actually setting the mixed layer properties. However, it's not the mean or integrated amount of heat fluxes due to colder outbreaks, but rather their distribution that really affected the final mixed layer properties. So we had the first cooling and then the deepening stage of the mixed layer. And here it was really important that we had this constant forcing because of, at this site, the ocean advection that kind of shows the mixed layer in between. And then finally, we showed that the Egwin offset, there is a connection to the North Iceland slope, and there might be some pathways how this dense water is kind of moved around, but this passage itself is definitely no major pathway for the dense water. Okay, I'm happy to take any questions. Thank you.
Great, thanks, Stefanie. I think we have time for questions.
I see, John, you put your hand up.
Just wanted to comment. Nice presentation. You want to tell the folks a little bit about the project that Bob Pickert was telling me about the other day of a new moored array for the IFSJ?
Yeah, that's right. So he just got funding from NSF to deploy a mooring area here across this Iceland Faroe Ridge, where we then actually want to study this Iceland Faroe Slope Dret more. So what we've had 1 cruise where we kind of then identified this current, but now we really want to know more about its variability and everything. So yeah, very cool.
Okay. Hi, this is Janis Kalling talking. I was just wondering if you had any sense of the decadal, like longer term variability, because I know in the Greenland Sea it can vary a lot, like how deep the convection goes. So do you know?
Yes.
That's okay.
So I'm
That's
prepared
the
for
answer.
that. Of course, we have only 2 years of mooring data, right? So how can we know, how does this fit into the large scale context? So here I'm showing the CS concentration at the mooring site over kind of the last, from era 5, kind of from 1950, and then how our winters fit into this. So they, of course, only in the recent winters, kind of maybe after 2002, we can see that really the sea ice has gone, and then we can kind of actually compare the years. And yeah, so then the turbulent heat fluxes were kind of, they are similar, but still this led to kind of these significant differences. Maybe the second winter is rather on the weak side compared to overall, like when the sea ice was gone. But I think they're kind of at least representative now for the times that we are in. Yeah.
This is Jamie Morison. Yeah, that was a nice talk. I'm curious. We used to hear a lot about really deep convection in the Greenland Sea, and does that happen anymore?
No. So deep convection in the Greenland Sea has kind of ceased in the 1980s or so. So now we are not forming the really deep, and that really dense water was actually also too dense to cross the ridge, right? It was actually too dense. Now we are forming a new class of what's called Greenland Sea Arctic intermediate water in the Greenland Sea, and this is really what is now the main kind of what's being exported now across the Greenland-Scotland ridge. Yeah.
Oh, wow.
But it's not this really deep convection anymore.
Yeah. So does that, this seems like that would have a big impact on AMOC and all that kind of thing. Is that not true?
Yeah, so I mean, I guess that the really dense water again was not exported across the ridge because it was too dense back in the
okay.
80s. So then the Iceland Sea was more important because there we formed slightly less dense
Yeah,
water.
yeah.
So now kind of the roles have maybe shifted a little bit from what the importance of the Iceland Sea compared to now it's the Greenland Sea that supplies kind of the denser component.
Oh, okay.
So things are definitely shifting, yeah.
Oh, that's helpful.
And now actually also with the retreat of the ice edge kind of across the East Greenland current, we may also densify the water as it progresses along, right? It's not only exposed to the atmosphere on the eastern side, but now actually also on the western side. So we may form denser water now in the boundary current system again. So things are really changing now. Yeah.
Yeah. Fascinating. Great.
Patrick, I see you have your hand up. You could get the last question here.
Yeah, thanks. A great talk. I have a question. I thought to remember a paper by Thor Eldevik and others around 2011, where they looked at the inflow-outflow variability and trying to connect the role of the outflow across Denmark Strait that's related to the boundary current water mass transformation versus Greenland Sea, and they concluded that Greenland Sea, so deep water convection, is not a major driver of that variability. How does that fit with what you just described?
Yeah. So I guess to Eldevik's paper, that's from 2009, and that was kind of before this North Atlantic jet was discovered. So the main paper there was 2011, and then of course no one knew about the Iceland ferro slope jet until about like 2 years ago. So I think we've kind of learned a little bit more about where this dense water actually comes from. And of course, variability can be set differently, but in terms of at least the volume export, we know that the North Atlantic jet supplies about a third up to a half to 50% of this overflow. And then the Iceland ferro slope jet also about 50% of the volume transport of the Faroe Bank Channel overflow. So these currents are certainly important. And we know that this dense water is certainly not formed in the boundary current because it can't get as dense there as in the interior Greenland seas. So I would put some question marks on that paper now, based on what we've learned recently.
Well, thank you. Thanks.
Thank you again, Stefanie.
Okay, our next speaker is Emily Hayden.
So my name is Emily Hayden. I'm a PhD student at Oregon State University. And today I'm going to be taking us on a bit of a topical and regional departure and talking about variability in atmospheric circulation over the Bering Sea and how that impacts air sea heat fluxes in the region. Okay. So just a little bit of background. Many of you are probably aware of this, but air-sea interactions are important to understand in the changing climate, particularly at high latitudes, because those are experiencing cellular rates of change, as many of you know. So aspects of changing ocean-atmosphere interactions at high latitudes remain poorly understood, but we're getting this increasing awareness of some of the severe and long-lasting ecosystem impacts that they can have, marine species mortality, altered marine biodiversity, and the like. So my goal in this work is to assess how heat exchange between the ocean and the atmosphere is affecting ocean temperature anomalies, and I'm emphasizing the Bering Sea. And so my study region is shown in the figure on the left-hand side, and that's bounded to the north by the Bering Strait and to the south by the Aleutian Islands. And this region is interesting because of the complexity of the ocean atmosphere and sometimes sea ice interactions. And some examples of some key coupled processes are sea ice formation. Seasonal sea ice formation in the region is driven by atmospheric forcing, so the net air sea heat fluxes and wind-driven advection of sea ice. The wind direction and magnitude is a strong driver of ocean circulation variability in the region. And ice cover is really important because it allows cold Arctic air to remain over the region in the winter, resulting in a positive feedback between sustained ice cover and the overlying cold air. So some recent coupled ocean atmospheric streams over recent decades, particularly 2010 to present in the Bering Sea, that are driving my research interests. So there's been extreme low sea ice extent observed, with 2017 and 2018 being the lowest on record at 47% of the climatological mean. There's also been a significant warming trend that's shown in the figure on the left-hand side, with an increase of over 1/10 of a degree per year in sea surface temperature anomalies over the ice-free Bering Sea. And finally, there's been increased heat flux variability and an increase in heat flux anomalies over the same time period. So recent work has discussed some of these changes as possibly indicative of a regime shift beginning in 2017 and as an indicator of a system-wide shift. And this has been characterized by exceptional anomalous atmospheric conditions. And the figure on the right-hand side is showing the January, February, March sea level pressure over the Bering Sea. And the upper panel shows 2012, 2016, the lower 2017 to 21. And this is showing a shift in the Aleutian low in recent years. It has shifted toward the northwest and is driving increased southerly winds. Okay. So building on work that's analyzed some of these recent Bering Sea extremes, we developed the following research questions. The first is, what's driving these observed heat flux anomalies in the region, and how are they affecting the coupled ocean atmosphere system? Second is, how are intraseasonal and synoptic scale or storm scale atmospheric circulation events affecting heat flux variability and temperature distribution in the ocean and the atmosphere? And finally, are anomalies in the ocean driving anomalies in atmospheric circulation, or atmospheric circulation anomalies driving anomalies in the ocean? And this is a really quick just reminder. I'm sure most of you are aware of this, what air-sea heat fluxes are, but I think the key things to note on this are that in this talk, I'm going to be referring to positive heat flux anomalies as into the ocean or warming fluxes, and negative heat flux anomalies as out of the ocean or cooling fluxes. So some of these questions remain open in part because the Bering Sea is a remote region with extreme weather conditions, particularly in wet winter, and that's historically led to poor data coverage. In particular, we have minimal in situ measurements of surface heat fluxes. However, reanalysis products are a nice way to begin to understand some of these air-sea heat flux dynamics. So in this talk, I'm going to be using the ECMWF ERA5 reanalysis fields to analyze the physical drivers of the observed heat flux anomalies, focusing primarily on the contribution of wind variability on those anomalies. So a quick background on the region and the climatologies of the heat fluxes there. So climatologies are computed for the 1981 to 2010 base period, and these figures show the climatology of the net air-sea heat flux over the Bering Sea. The upper panel is the seasonal climatology of the net heat flux in watts per meter squared, with the gray line showing the climatological average sea ice extent over those months covered. And the lower panel shows the spatially average daily mean of the net air-sea heat flux climatology in black, and the components of that shown in the other colors. So this depicts the seasonal cycle of the air-sea heat flux in the region and shows that the Bering Sea generally acts as a heat sink in the spring and the summer and a heat source in the fall and the winter, and that it tends to be, or that it is dominated by the shortwave fluxes. So the first part of the analysis was to investigate when the net heat flux anomalies were strongest and evaluate what component was driving these anomalies. So this figure in black shows the spatially averaged over the Bering Sea domain, which is noted in the upper corner as a reminder of the net monthly heat flux anomalies over the ice-free region. The red shows the turbulent contribution and the gray shows the radiative contribution. So from this, we can see that the strongest air-sea heat flux anomalies are in the fall and the winter, coincident with the sea ice season, and during the fall and the winter, the turbulent component, or the red, describes the majority of these net heat flux anomalies. So we looked at this in more detail by splitting the turbulent heat flux anomaly into the sensible and the latent contribution, and that's shown in the figure on the right-hand side. The sensible heat flux anomalies are shown in red, and the latent heat flux anomalies are shown in gray. And during the fall and the winter, the sensible heat flux anomalies tended to be larger than the latent heat flux anomalies, and particularly over the last few years. Okay. So then we wanted to assess the dominant driver of the wintertime turbulent heat flux anomalies shown on the previous slide. So ERA5 computes the heat fluxes using Mohn and Obukhob's similarity theory, and that's fairly difficult to replicate on a smaller scale. And it's more straightforward to compute the heat fluxes using a bulk flux algorithm method, and that's shown in the two equations near the top. And we found that that replicated the ERA5 heat fluxes quite well. So we computed the turbulent heat fluxes using this bulk algorithm shown in the bottom equation, and then we can decompose that into terms of atmospheric circulation, thermodynamic variability for the sensible heat flux, and specific humidity variability for the latent heat flux. So for the remainder of this talk and in this slide, anomalies are denoted by primes, climatologies by overbars. And if you look at the first equation on the lower part of the slide, the sensible heat flux, when we do this decomposition, we find that it's a function of terms related to climatologies and anomalies in wind magnitude and the air-sea temperature difference. We have a similar result in the lower equation for the latent heat flux, and it is a function of wind magnitude and air-sea specific humidity difference. So we can use these decomposed turbulent heat flux anomalies to evaluate the impact they have on ocean temperature, as well as the atmospheric forcing of the observed heat flux anomalies. So in this figure, there is a plot of the total sensible heat flux anomaly and each term of that decomposition over the spatially averaged ice-free Bering Sea. The upper panel shows this total sensible heat flux anomaly. And from fall 2014 to 2020, the anomalies have primarily been positive and therefore are acting to warm the ocean. If we look at the second part of the panel, this is the term in the decomposition that's related to the air-sea temperature difference. And this shows that the main contributor to these sensible heat flux anomalies above are due to anomalies in the air-sea temperature differences. So we can break this down even further into the term related to the air temperature anomalies and the term related to the sea surface temperature anomalies, and that's shown on the right-hand side. And the upper panel shows the air temperature anomaly term, and from this we can see that sensible heat flux anomalies are primarily driven not only by anomalies in the air-sea temperature difference, but this is primarily due to air temperature anomalies, specifically positive air temperature anomalies. And if we look at the lower part of the figure on the right-hand side, we can also see that sea surface temperature anomalies have tended to be positive over this time frame. And so we are having some flux from the ocean into the atmosphere, but this has been too small to overcome the ocean warming due to the atmospheric forcing. So also looked at the atmospheric forcing of the latent heat flux anomalies, and we see something fairly similar. So again, we have the plot of the total heat flux anomalies and each term in the decomposition. And the top is the total anomaly, and then we have the term related to the air-sea specific humidity difference in the second one, and then the other terms below that. And we can see that the air-sea specific humidity difference anomaly term is the one that is primarily driving the observed latent heat flux anomalies. So again, we can separate this into terms of the specific humidity anomalies at the ocean surface and in the air. And we find that the air specific humidity anomaly, which is shown at the top part of the right-hand side, is the majority driver of the observed latent heat flux anomalies. So from these results overall, we can see that warm, moist air anomalies are driving the majority of the observed wintertime turbulent heat flux anomalies in the Bering Sea. So since these are driven by warm, moist air anomalies, I wanted to evaluate what role the wind direction plays in driving these. So all of these figures are showing the sensible heat flux anomalies and the decomposition components, and these have been bin averaged according to the anomalous wind direction, which is denoted by theta prime. So the thing to note here is that when x equals 0, we have westerly wind. When x equals pi over 2, we have southerly wind. So we're going to start on the left-hand side in the upper panel. This is the total sensible heat flux anomaly. And the thing to take from this is that there's a pretty nice sinusoidal relationship from the sensible heat flux anomalies in the wind direction. So when we have southerly winds or winds at pi over 2, these are associated with the strongest positive sensible heat flux anomalies. And the mechanism that we're proposing for this is that advection of warm air from the south. And we saw that this warm air is a key driver of these sensible heat flux anomalies, is leading to decreased ocean heat loss and an increase in the positive sensible or sea surface temperature anomalies. So we can also see this in the figure also on the left-hand side on the lower part of the slide. And this is the term in the decomposition of the sensible heat flux anomalies that's related to the anomalous air-sea temperature difference. And again, there's a pretty nice sinusoidal-ish relationship with the wind, with southerly wind acting to advect warm air anomalies that are driving the majority of the positive sensible heat flux anomalies. If we look at the figures on the right-hand side, these are the other terms in the decomposition, and from this we can see that there isn't a very clear relationship to the wind that's driving these components. Okay. Very similar to the other side, but this is again for the latent heat flux anomalies. Again, starting with the total latent heat flux anomaly in the upper left, and then we have the first term related to this specific humidity difference anomalies. And again, there's a pretty nice sinusoidal relationship between the latent heat flux anomalies and the wind direction, with southerly wind associated with the strongest positive latent heat flux anomalies. And there's a similar sinusoidal relationship for the term related to the specific humidity anomalies. Just to kind of summarize where I'm at right now, some of the things that I'd like to look at in the future. The wintertime air-sea heat flux anomalies are dominated by the sensible and latent components, and I'd like to look at what role these play in sea ice loss. Other work has shown that southerly wind anomalies are really important for driving sea ice out of the Bering Sea, but I think that there might be a little bit more to that, and that the wind is also acting to add heat to the ocean, which might be interacting in some way with the sea ice to further decrease. Warm moist air anomalies are responsible for the turbulent heat flux anomalies that are contributing to ocean heating, and I'd like to evaluate how much of the observed ocean warming these are responsible for. And finally, wind direction plays a key role in driving the turbulent heat flux anomalies, with positive anomalies associated with southerly winds, with anomalous southerly wind. And in the future, I'd like to evaluate how wind anomalies related to intraseasonal and synoptic scale, how these wind anomalies are related to changes in intraseasonal and synoptic scale atmospheric circulation, and what the relationship is to the broader atmospheric circulation. With that, I'll take questions.
Great, thanks, Emily. Questions?
This is Dmitry. Thank you for the presentation. Can you go back one slide, please, to your conclusions? Yeah. Number 2 and 3. So it seems to me that 2 and 3 are related. Don't you think that, for example, northerly winds will bring less moist air, and southerly winds will bring more moist air? So isn't it the same? I mean, point 2 and 3. I think what I'm trying to say is that wind direction obviously plays a key role, because you say this already in point 2. So I don't think it's necessary to distinguish point 3.
Okay.
It's a question. Do you agree or disagree? Thank you.
I think I see where you're coming from. Yes, the wind direction is really important for bringing the type of anomalies that we're seeing. In that, yes, when you have wind that's blowing from the south, the air tends to be warm, it tends to be moist. So yes, I can see why you're saying that these are maybe similar, or if not the same. I think that I am separating them because we are still kind of trying to evaluate exactly where the warm moist air anomalies are coming from. So it seems like they are related to the southerly wind, but I'd like that maybe I should talk more broadly. I'm interested in looking at where those are coming from in the broader atmospheric circulation outside of just the region of the Bering Sea.
I see we have a question online from John.
Very nice presentation. You showed us how the climatological atmospheric low shifted west. I mean, is that the principal mechanism by which you're now getting warm, moist air advection from south. You're on the right side of that low pressure.
Yes, some previous work has talked about how the shift of the Aleutian low is the primary reason that you're having the southerly winds that are blowing into the Bering Sea. However, some of our initial work is finding that it may not just be the wind that is blowing directly from the south, that there might be a larger atmospheric circulation pattern that is bringing warm, moist air that is not necessarily just directly from the south, but we're seeing that it's blowing from both the southwest and the southeast. And so ultimately, the Aleutian low is really important for directing which, or for determining which direction those anomalies blow over the Bering Sea, but where those are coming from is more variable.
Right, and that Aleutian low is basically this net sum effect of lots of synoptic storms coming by, and so you're probably thinking now about what the storm track does and why that varies. So good work. Thanks.
Hi, this is Yunju. Just a quick question on the technical thing. When you calculate heat fluxes, how do you treat the sea ice coverage area for wintertime?
Yeah, so the sea ice question is a really interesting one that we're talking a lot about in our group. What we're doing right now is we are masking out the sea ice. And the reason for doing that is because there has been some work that has come out that has talked about how ERA5 and other reanalysis products have a difficult time capturing the heat fluxes over the sea ice. And so we don't feel comfortable including those in our analysis right now because we're not really at the level we want them to be. So what we're doing is we're just masking out the sea ice and only looking at the open ocean area and then trying to account for changes in the open ocean area by taking spatial averages. But that is a big thing that we're thinking about right now is how do we account for the things like the sea ice edge and the impact that has on the air sea heat fluxes.
Thank you.
Robert, you get the last one.
Last one, we'll wait here. Some people in my group, they argued that the surface exchanges are influenced by geochemistry, by film of organic molecules basically at the surface. Is that something that you are concerned about?
That is not something I considered before, but it's certainly interesting to think about, is the idea that if you have these films, it changes things like the diffusion of heat at surface.
Mm-hmm.
Is that kind of the mechanism that your group is considering?
Yeah, I guess so. I mean, those layers of the organic molecules, they affect the surface roughness, for instance, and affect the turbulent transfer of heat and other properties across the surface. And Bering Strait is obviously or Bering Sea is obviously a very productive region, so where you might expect effects like that to play a role.
Mm-hmm. Yeah, and I think that in some ways this is a bit suggestive of some of the issues of using the reanalysis heat fluxes in general, is that they're useful for getting a pretty general sense of what's going on in the region, maybe getting some idea of what we think some of the key drivers of these are, but then when it comes down to it, they're not accounting for things like that. ERA5 is not accounting for that type of change in the surface. And so this analysis is primarily to drive future work to look at things like changing atmospheric circulation and maybe getting away from the heat fluxes themselves because there are issues with those, and that is a good thought.
Thanks.
Okay, excellent. Thanks again, Emily. We're going to go back over to the Greenland side now with Mike Wood.
All right, excellent. Hey everyone, my name is Mike Wood. I'm a postdoc at NASA's Jet Propulsion Laboratory. And today I'm going to be talking about linking changes in the regional ocean around Greenland to Greenland's land ice loss. And specifically, I've come to this community to make a case for sustained ocean observations on Greenland's shelf. And so I guess I come as an ambassador for the land ice community, but also represented in this work are Josh Willis and Ian Fenty, who are actual oceanographers. So there's some support there. So hopefully when I'm going through this talk about glaciers, you have something like this in mind. This is Helheim Glacier. It's in southeast Greenland, and it's one of over 200 glaciers in Greenland that are transporting ice from the interior of the ice sheet outward toward the ocean. In this picture, the interior of the ice sheet is back in the distance, and the front of the glacier here, which you can see in the foreground, is constantly breaking off huge icebergs. These have keel depths of several hundred meters, and then they float out into the regional ocean. So this is hopefully what you have in mind. There are, again, over 200 of these glaciers in Greenland. So it's been a long conference workshop, so I'm just going to put my pitch right up front, and then I'll circle back to it. But I really think that autonomous profiling floats could be a really great way that we could continue these important observations on the shelf. So we've done some experiments deploying these Argo-like floats on the shelf, and you can see some of the parts here in Northwest Greenland in the red dots where we've deployed these floats. And these floats can be parked on the bottom, which is really important through the wintertime because there's ice cover on the top seasonally. So these floats allow us to get observations through the wintertime. They give profiles that look like this. We're still waiting on the return of some data for the winter of 2022. But hopefully these plots convince you that we can get full season observations from these floats, and they stay in particular areas there. When you're looking at plots like this, especially in conjunction with the first talk we saw today, you might be thinking, well, why not moorings on these shelves? And that has to do with the ice environment around these. So all of the glaciers in Greenland are discharging these icebergs that have keel depths of several hundred meters, and they're really good at finding moorings. People have tried to put moorings in these areas, and they always get clobbered and destroyed. So having a float that can hide out from underneath all of these big glaciers is really beneficial for this type of environment. Okay, so why are ocean observations so important for what's going on in the land? So here I'll give a little primer about the changes that we're seeing on the Greenland ice sheet. So we have a number of ways of measuring Greenland's ice loss. One of those ways is to look at changes in elevation. And we can do that by differencing, for example, elevation measurements from ISAT and ISAT-2. And when we do that, we can see that Greenland is currently losing about 300 billion tons of ice a year. This has contributed more than 14 millimeters to global sea level rise since the year 2000. And we can get a sense of why that is happening by looking at where it's happening. So you can see in this map that Greenland is losing most of its ice around its periphery. So there is an atmospheric signal in here. As Arctic air temperatures warm up, these areas on the periphery of the ice sheet are at lower elevation, and they're starting to see the anomalous surface melt first. But also, at the periphery of the ice sheet, that's where all of the fastest flowing ice is found. So those 200 glaciers I mentioned, this is where they're located. And what we've seen in the last few decades is that those glaciers are flowing faster, and they're discharging more of their ice into the ocean. And this is causing a drawdown of the mass at the edges. So this is where the ocean comes in and its connection to the land ice. So it's no surprise to anyone here that there's a network of currents that takes warm, salty Atlantic water from the North Atlantic and distributes it around Greenland. That warm, salty Atlantic water layer, which is deeper, can get across the Greenland shelf and in through the fjords where it can there melt the glaciers. I have a little movie here. It's narrated by Josh Willis, and I don't want him to talk through my talk. So, great. We can't hear him in the room. Hopefully you can't hear him online. But when we're thinking about how the oceans melt the glaciers, it's helpful to think about what's going on upstream of the glacier. So we have a lot of surface melt on the glaciers, and this actually finds its way down through the glacier by melting through cracks and things like that. And so it finds its way to the bottom of the glacier, and it actually runs off underneath the glacier into the ocean. So what we get is a scenario where we have this fresh water, which is discharged hundreds of meters down in the ocean. And of course, that water is subject to strong upward buoyant forces, right? So this creates a turbulent plume that entrains that warmer Atlantic water, and it creates really intense melt on the undersides of the glaciers. this undercuts the ice above it, and it causes the ice above it to break off in a process we call calving. So this process, which is breaking icebergs off the front of glaciers, has been enhanced in recent years because we're seeing a warming of the waters around Greenland. So this is how the ocean around Greenland is directly connected to what's going on in the land ice. So if you wanted to calculate that process for all of Greenland's 200 glaciers, you would need two really important measurements. One is the depth of the fjords, because this tells you whether that warm water can make it in there. And you also need to have an understanding of what the temperature is actually inside the fjords. And so this was one of the big ideas behind a recent NASA mission called Oceans Melting Greenland, or OMG. So OMG was primarily an airborne mission aimed at understanding this process, how the oceans are melting Greenland. And one of the biggest components of this mission was to do an annual survey using airborne CTDs. And we deployed CTDs, more than 250 of them each year, at these yellow dots, which you can see on the map on the right-hand side. So we primarily did this in the summertime, and this was supplemented by ship-based measurements, which we did in 2015 and 2016 in conjunction with some bathymetry measurements as well. So what did we get with all of these measurements? Well, one of the big results from our OMG campaign was published last year, and it was a paper about how, well, it was reflective of this process which I just described, how the oceans are forcing the glaciers to retreat with this enhanced melt. And so what we found is that as the water started to warm around Greenland, sort of at the start of the century, the glacier retreat rate started to really increase, and we linked this to that melt process I was mentioning before. So this increase in ocean temperature is related to anomalies in the North Atlantic, and then also to a shift in the North Atlantic Oscillation. What we also noticed is that about a decade into the century, around 2010, there was another shift in the North Atlantic Oscillation. The temperature around Greenland cooled slightly, and we saw the retreat rate of the glaciers temper off. So they're still retreating, but at a lower rate. The main takeaway from all this is that the glaciers in Greenland are extremely sensitive to what's going on in the ocean. And so measurements of ocean temperature are really key for helping us understand how the glaciers are going to continue to evolve and what their sea level contribution will be. So OMG just finished up last year, so there will be no more surveys like we did. And so now when we're thinking forward about the glaciers in Greenland, we can ask, what are the available observations that we have on the shelf? And it turns out that on Greenland's shelf, the sampling is really sparse and sporadic. So you might think, well, what about the Argo Array? We have hundreds of these floats around the ocean. A lot of them are in the North Atlantic. And so I just did a query, or Josh Willis helped send this data to me. It's a query of all the locations of the Argo measurements that are around Greenland. And what you can see is that, yeah, they get close to Greenland, but it's pretty rare that they ever make it onto the shelf. And this is because the Greenland shelf is maybe at a maximum 1,000 meters, more like 500 meters. And these Argo floats, which are floating around at deeper depths, can't get onto the shelf. So really what we're left with when we're thinking about Greenland shelf waters is sort of irregular PI cruises that are subjected to who gets funding or global pandemics, things like that. So for thinking about sea level rise, it's really critical that we have some way to continue these observations on the shelf. And now we're circling back to this initial pitch that I gave, that I really think that these autonomous profiling floats are a viable way to go for us to continue to monitor the Greenland shelf waters and to link those changes to what's going on in the glaciers. So we did a little bit of experimenting with different types of floats during the OMG mission. Specifically, we use these two types of autonomous floats, which can be air deployed or ship deployed. One is an Alamo float, which is created by MRV. These cost about $25K. And the nice thing about these floats is that they are quite compact and can be deployed from an aircraft through a chute in the aircraft, which is nice because you don't have to open the door. to throw it out. So during OMG, we purchased 17 of these. So far, we've deployed 15. We have 2 more headed to Greenland this summer as part of some opportunistic collaborations. And from those 15 that we've already deployed, 9 returned data. So we're missing some data from some of those that are already deployed. We also experimented with an apex float, which is created by Teledyne. These have a similar cost, but they're a little bit bulkier. So if you're going to air deploy them, you have to open the aircraft door and push it out. I'll have an image at the end of how bulky these things are. During OMG, we purchased 6 of these, deployed all 6, and we heard back from 5. So a little bit better track record with the apex floats versus MRV. Okay, so I've come here to give a pitch about how we should deploy these floats, probably guessing or wondering where I think we should do this. So since we want to use these floats to study how the glaciers are going to evolve and for sea level type studies, one of the criteria for choosing the location should be, where are the glaciers and which ones are contributing substantially to flux and mass loss from the ice sheet. I should have a color bar on this map. But hopefully you can tell. So this is a map of the Greenland ice sheet velocity, and the really fast moving ice is shown in the blues and pink colors. So these are the glaciers that flow the fastest. They're also the ones that are most susceptible to melt from the ocean and also contributing to sea level rise. So a lot of these glaciers have popular names. These are names of some of the really big players. But you can see that they're on both sides of the ice sheet there. Right, so these should be sort of our targets for where we're deploying floats nearby. But of course, if you're deploying floats on the shelf and you want them to stay there, you should think about what the local currents are and what the bathymetry looks like. So a good criteria for deploying these is the ability for it to stay in one spot. And then also think about what the so also it doesn't make sense to deploy 2 floats in the same area that are essentially measuring the same water. So it's good to think about what's hydrographically unique on the shelf. So putting all that together, I have 8 sites where I think that these could make a big impact. So here we're looking at a bathymetry map of Greenland. I've saturated the color bars so that everything below 500 meters is blue. And what shines out of this is that on the left-hand side, or the west side of Greenland, there's 4 really big troughs that come out in those dark blue colors. On the right-hand side, there are also a number of troughs. 4 of them are quite large, and these link up with those 8 glaciers, which I mentioned before. So I point to these different parts on the shelf here, and these are sites that would be amazing to have these floats to understand how Greenland's glaciers are going to change. As I wrap up, I just wanted to give a few final thoughts on how I think this will work. So the who, the when, and the how. So for this effort, what we're imagining is an international collaboration of scientific institutions that are involved with getting these floats deployed. And this would be similar to the support for the Argo program, which has a lot of players involved. We would envision that these floats would be deployed in the summertime to replace instruments which are lost or getting old or discharged from the shelf, things like that. And these can be either deployed from the air or ships. So we can really leverage flights of opportunity, cruises in the area, and things like that if we have a good network of collaboration and folks who are thinking about this as well. And this is actually what we're doing this summer with the 2 remaining floats that we currently have. So final takeaways, ocean observations on Greenland shelf are important for understanding, quantifying, and also projecting sea level rise. Currently, these observations are quite sparse and really only conducted in the summer right now. And I think autonomous profiling floats similar to Argo are a definitely viable way to provide these continuous observations. So with that, I'll take questions. Thanks.
Great. Thanks, Mike. Questions?
Thanks, Mike. That was a really cool talk. And I was just wondering if you could tell us a little bit more about the floats. Like, it sounds like they're able to keep position, but I was wondering how that works and also how frequently they profile and also how much they cost. Thanks.
Yes. So I'll walk it back in the order that I remember it. How much they cost? They cost about 25K, these ones. Potentially if more are purchased or if they don't need to be air deployed. I suppose that could be, the cost could be alleviated, but for now, 25K is the answer to that. The period at which they sample can be programmed. So when we deploy these, we typically have them sample once every hour for the first, 6 hours so that we can ensure that they're working. And then we put them into, I think, a 5-day mode is what we have for most of them. And then how they stay in one spot is we deploy them in areas where from bathymetry maps we can see that there are sort of bathymetric contours that would hold it in one spot. So they not only park on the ocean floor, but if they drift a little bit, we try to put them in bowls and things like that in the bathymetry so that if they do drift a little bit, then they sort of stay in one area. And we've had good success with that for many of the ones we've deployed.
And one more quick thing. Why do you think the Apex floats had better return? Do you have ideas?
Yeah, so we had a few troubleshooting things to figure out in the field. One of the things that we've found out is that some other labs have folks that are quite good at sort of babying the Alamo floats a little more, so that they can have better returns. But one issue that we ran into was that they weren't designed for unpressurized aircraft. So in the past, they had been deployed from C-130s, which are pressurized. We were using a DC-3, which is an old aircraft, and it was unpressurized, and this caused some issues with the pressure bladder inside the Alamo. So we discovered that later on, unfortunately. But I think there was some issues with the pressure bladder in some of our initial deployments.
John, I saw you had your hand up.
Yeah, nice technology and presentation, Mike. So these bottom resting floats are great technology for all shelves, I think, in the Arctic. With the Apex that have actually a CTD on board, have you looked at what the connectivity does when they sit in the mud for hours or days on end?
I haven't looked specifically at it, but we haven't noticed any big anomalies that would suggest that. Are you thinking that silt is maybe staying in the conductivity meter and that it would give anomalously low salinity values?
It could.
We haven't seen that, but it's
probably you're looking at signals that are hundreds of times bigger than small errors that could come in.
Yeah, right. So we've our AXCTD, the AXCTDs that we use for the OMG survey, we would monitor the conductivity on those, and it was very clear when those were stuck in the silt. So we haven't seen anything like the signal that we saw in the AXCTDs on the Alamos or Apex, but it's certainly something to keep in mind.
Thanks.
Yeah, this is Jamie. Nice talk, Mike. And full disclosure, I'm an OMG fan and fundee, but in the context of this meeting, absolutely. I mean, it seems to me that this is about the subarctic seas in addition to the Arctic Ocean. So I think this really is an important part. A lot of our justification for studying the Arctic Ocean are the downstream feedbacks that or repercussions of changes in the Arctic Ocean. And we often, when we're trying to justify activities, talk about, well, things are going to be causing changes in the deep convection, and the changes in the Arctic Ocean will cause changes in the deep convection in the Nordic seas, and I usually say conceivably they affect the melting of the Greenland glacier. So it seems to me it's a natural part. And the techniques and technology are probably the same for working out in the Arctic Ocean, especially if we're trying to get into hard to reach areas. So it really makes perfect sense. And the other part of that is, of course, there was a NASA aircraft program that supported OMG with actual NASA aircraft. And so I'd be looking for, if we do this as a part of some Arctic Ocean thing, these techniques could be applied, and the aircraft that OMG has used could be used to do deployments in other parts of the Arctic Ocean and subarctic Sea. So it just seems like it's a natural combination. Thanks.
Great. Yeah.
I'm sorry, that was just a comment. I guess
I appreciate the comment. Yeah.
I'll say we're going to move into a general discussion now. So thank you again, Mike. And I'll pull up the WebEx people for everybody, but I know Cecilia had a question, I think probably for Mike. So
It's a very quick question. Are there, in addition to your 2022 opportunistic deployments, is there plans for OMG Part 2?
Not currently. I think a lot of the discussion is now maybe thinking about Antarctica and some of the similar data gaps, but similar processes as well going on down there. But currently no plans for, sadly, OMG 2.0.
Thank you. And Mike, while you're there, sorry. You showed this nice schematic video, cartoon video of calving. Do we have actual direct measurements of the subsurface plume?
Yeah, so there's been a couple papers where folks have taken multi-beam sonars and then turned them on their side, and then they do repeat pass of the glacier front. And from that, you can see exactly where, how the volume is being lost and where it's being lost. So we do see that volume being lost in the underside of the glaciers. And then for just visual imagery of the plume, a lot of times if the plume is strong enough, it can actually have a surface expression. So it'll reach the surface before it reaches natural buoyancy. And you can see it because it'll melt all the icebergs in the fjord, and it's just like a big bullseye right in front of the glacier. So we know that these plumes are strong and that they're going on, yeah.
Thanks.
Sorry, I think Patrick, do you have a question?
Well, if you have enough time, I do have a question regarding, you mentioned at the beginning and you pointed to the importance potential of the subglacial runoff as an amplifier. And some studies have actually shown that theoretical, it's hard to access, that this could increase melt rates by a factor of 10, like an order of magnitude. So if that was the case, what's the relative importance of the ocean temperature versus the seasonal or the interannual variability in that subglacial runoff as such an amplifier to actually cause, what's actually causing the interannual variations? Is it really the ocean temperature, or is it the atmosphere through subglacial meltwater supply and buoyancy supply?
Yeah, that's a good question. We did some sensitivity tests in our project, and we found that the majority of it, as far as Greenland was concerned, especially when we were talking about this shift sort of starting in the late 1990s, was primarily due to the change in ocean temperature. So like more than 90% was due to ocean temperature versus changes in the runoff. But that doesn't mean, I think that the study referencing was the one on the Kant Glacier in Alaska, if I'm not mistaken. And that glacier is more shallow, and there could be different changes in runoff there that could make the variations in subglacial discharge potentially more important than variations in ocean temperature for that one. So I think it depends where you look and when.
Right, but the one thing is the runoff itself the volume that it supplies, but then the other one is the amplifier for the melting, for the subglacial melting. So the amplifying effect of that of those melt rates.
Right, yeah, so there is an amplification based on increased runoff from the ice sheet. Yeah, there's no doubt. But when we're talking about several degrees of warming in the ocean versus 30 to 50% increase in runoff, peak runoff in the summertime in Greenland, a lot of this has to do with the ocean temperature changes.
Thanks.
Yep.
Hi, Mike. Marion Alberti here. Thanks for the nice talk. I had a kind of practical question about the fieldwork. So everything that you presented was done from airplanes. Is there any reason there's no ship-based component? And then kind of related, is there an interest in getting sustained velocity observations on the shelves to understand just like how current variability comes into play?
Yeah, having more velocity information would be great. It's not something that we explore during OMG, but yeah, more data is good data in my mind. But as far as the ship deployments, maybe I brushed over it a little too quickly. There was a ship component to OMG. So we did bathymetry mapping on the northwest coast, primarily during 2015, and on the southeast coast during 2016. And as part of those bathymetry surveys, we also did ship-based CTDs for that whole time. And in the later years, we actually deployed a few of these autonomous floats from the boats as well. So there's certainly a space for you can do this from boat very easily. Yeah.
Hey, everyone. And remember, we can also give Mike a break and talk about deep convection in the Iceland Sea and also the Bering Sea as well.
Sorry, I'm not going to give Mike a break. Well, maybe I am going to give a break, but I mean, I guess relative to the last question, the temperature of the fresh water that's coming down under the glacier and coming up, I mean, it's really cold. And if it was just that water and it's coming up the side of the glacier and the freezing point is warming up, it seems like that would probably not melt much ice. I mean, the only reason it's right, I mean, if it was just all fresh water coming up, it seems like that wouldn't melt much ice.
Yeah, you're right about that. But it does melt a bit. There's turbulence, but it is entraining water. When the fresh water comes out from underneath the glacier, it makes this turbulent plume, and it is entraining water that is warmer than the ice. So this plume action causes enhanced melting on the
I'm just saying
yeah.
the heat comes from the ocean. It doesn't come from this water that's at the freezing point.
Right.
Dimitri.
This is Dimitri. I have a question for Stefanie. In 1990s, 1980s, there were several studies by Norwegian and Iceland scientists who showed the relationship between ice formation in Iceland Sea and Greenland Sea and deep convection. And they were talking about Odin event. And it was a good indication that there is no deep convection happening in Iceland and Greenland Sea. So now, according to your presentation and some other studies, there is no deep convection happening in the Greenland Sea. Correct? Right? At the same time, Odin event hasn't happened since, I remember correctly, early 90s. So what's going on? Is the previous idea was wrong or something else is going on?
Yeah, so I think I would distinguish between deep convection and convection to intermediate depth. So previously, kind of up to the 1980s, we had really deep convection, and that was kind of then too deep or too dense water to actually make it across the Greenland-Scotland ridge. So now we are forming, and this is why the Iceland Sea previously was more important, because there we actually formed dense water that sank down to these intermediate depths that kind of can cross the ridge. And now with kind of this Odden ice tongue that has disappeared from the Greenland Sea, we get kind of formation of this more like intermediate water that actually makes it across the ridge. So this is now the Greenland Sea is more important. So I guess there's this balance of how close to the ice edge you are, like where exactly is the ice edge? Is this kind of located where the gyre is, where you have kind of this weak stratification of the water column to start with? And then the interplay of kind of what is the sea surface salinity also in the summer before. So it's not just as simple as I may have shown it. Okay, it's the ice edge. This is where convection happens. That is certainly not true. But kind of I think the processes have changed. Kind of what is that sets the convection and what kind of that kind of reach the depth that actually makes it across the ridge. If that helps.
Yes, somewhat, but I still don't understand why Odden, why we don't observe Odden ice event anymore.
So I think we may not have I don't think we ever have really understood why this Odden ice tongue forms and what caused it. So this is really like not the ice edge going straight down, but kind of a tongue of ice that sticks into the Greenland Sea. And I'm not sure we really have understood the formation mechanism of why this actually happened. It's just that recently, the past decades, this just hasn't formed. But I guess that has just to do with the general retreat of the sea ice edge as well. It's much harder to form sea ice in the interior of the Greenland Sea. But
I guess that answered my question then too. So do you think it's a kind of a permanent change in the system, or could it be something like with the Southern Ocean polynyas that maybe there is some really long time process of recharge or so that is happening there too, and that at some point the really deep convection might set in again?
I doubt that the really deep convection might set in again, because then again you would need more ice again in the interior Greenland Sea, and with the ice retreat, this is kind of not really going to happen. So I think rather the processes are changing. So instead of this deep convection in the interior basins, now we shift more to the boundary current system, right? So this is where we now might ventilate the Atlantic water even further. Unless we really change climate to get kind of the sea ice back, I don't think this is reoccurring soon. Yeah.
Also a question for Stefanie. This is Marian Alberti. I'm going to show my ignorance on the Atlantic side, but you talked a lot about how the changing sea ice edge is changing where all the heat fluxes are happening. Could you speak a little bit about the changing sea surface salinity and how that, you mentioned it when you were replying to Dimitri, and I guess I just was hoping for a better understanding of how that sea surface salinity signature is changing and the role that that plays as well.
Yeah, so we know that we have now more Atlantic water flowing into the Nordic seas, and it's also becoming warmer. And this means just we have more salinity in general, or like high salinity water. There's also like 3 different what we call domains. So we have this Atlantic side that is on the eastern Nordic seas, that is really this most saline regime. We have the cold polar freshwater on the East Greenland shelf, and in between, where we have the Greenland and Iceland seas, this is where we kind of have these intermediate salinities, and this is where we kind of get this dense water formation. And recently, it's been like this, that the salinity has increased, and I think this is mainly due to advection. I'm not sure we really know the processes, but then also we know that there's anomalies, right? We had like this great salinity anomaly in the 80s or something, where actually this freshwater blob circulated around, and that also then inhibited deep water formation because you get a more stratified layer. So I'm not sure if there's more to that.
Maybe to tie into what Mike was saying, we're talking about also with the freshwater coming off of Greenland, do we understand, like as that ice edge keeps retreating towards Greenland and Greenland starts putting out more freshwater, do we have a sense of like trying to maybe bridge the gaps between your 2 talks? Like, what's coming down the pipeline at us with those things?
So this is, of course, freshwater is really critical for deep water formation, right? If we get the freshwater into the interior basins, we kind of shut down deep convection. But then we also don't really know yet how much freshwater from the shelf actually makes it into the interior basins. So this is something that we actually are working on kind of right now to understand what's going on. So there are some indications and some studies that say mainly the freshwater stays on the East Greenland shelf or also the West Greenland shelf. And then we are good, kind of, right? As long as we don't push the freshwater into the interior, we can still form dense water there. So that's something we are still trying to figure out how sensitive is the system actually to a higher freshwater input on the shelf.
Stefanie, I think you said, the impression I got from what you said is that this deep convection in the Greenland Sea kind of happened last in the 80s, and that we've changed sort of regimes. That makes me perk up my ears because we've been arguing that we've been predominantly or increasingly in the cyclonic mode since 1990, and related to a shift in the Arctic Oscillation, which happened in 1990. Would you care to comment on the possibility that in the cyclonic mode, perhaps we're exporting more fresh water or liquid or solid into the Greenland Sea and kind of putting a lid on the deep convection in the Greenland Sea?
Yeah, I'm not so sure. Again, we need this process understanding of how the freshwater actually makes it in the interior, right? What we do know is that kind of the location of where this dense water is formed has changed. So earlier it was really in the when we had this really deep and dense water formation in the Greenland Sea. So before kind of the 80s, mid 80s, the water that was pulled to the ridge and to the overflows was formed in the periphery, because in the interior it was actually too dense to make it over the ridge. While now we are going, like, everything becomes lighter, so now it's more the interior Greenland Sea that's important, and this class of intermediate water that's formed. So I'm not sure this is only related to freshwater coming into the system. This is also related to how much heat loss is there with the atmosphere warming and the ocean warming. Kind of there's less cooling in general that happens, so everything becomes less dense. Yeah, I'm not sure how we can tie this to these circulation modes and the cyclonic mode, though.
Well, has somebody done a study to how does this relate to the NAO, for example? I don't know if.
So we have not really looked into this, I guess.
Okay.
Yeah, we are more concerned with the shorter times. I think some people say that, okay, this kind of fits with what NAO and kind of large scale signals are doing, but I don't know the details.
All right, that takes us to 10 o'clock, so we're going to wrap the discussion there. Thank you again to all our speakers. Our last round of speakers for the workshop. So we have a break until 10:20, and we'll reconvene for the report outs from our breakout sessions. Okay, so for breakout session 1, who's the elected speaker among the leads and note takers? It is Jamie Morison himself.
I'm back. Okay, well, this was kind of the first breakout session, basically about assessing what we know about circulation. And there were well, is there a way to switch this out of presenter? I can't read the print because it's too small. There we go.
Thinking about it.
Okay. Well, there were a number of, several of the groups mentioned local versus external forcing was one way of putting it. And then another way of thinking about it was there's basically two types of circulation, or two components to it. An estuary component that's driven basically by the height difference between the Pacific and the Atlantic, so that it pulls fresh water in from the Pacific, in an analogy to a river and an estuary. And then, of course, we've got the heavier Arctic Ocean, or excuse me, Atlantic Ocean water that comes in. And they exchange, controlled by topographic beta effect to have the circulation basically be counterclockwise. And then on top of that, we have a wind-driven circulation that we've talked about in terms of anticyclonic and cyclonic modes.
Sorry about this, Jamie.
I'm sorry.
It was going so well for the first 3 days.
And
okay.
If I had better eyes, I could.
Yeah, I think. Yeah, I'm not that good.
That's okay. Maybe we just have to do it if it is on.
That's it was.
Is showing.
It was one button.
Okay.
There.
Okay. And then the other issue that I think we all saw was the kind of the cyclonic versus anticyclonic circulation. And I hope that it came across that really this is just two sides of the same coin. And the upper ocean that follows this paradigm first put out by Sokolov in 1962 of these sort of anticyclonic and anticyclonic modes, in which basically, well, I'm going to flip over to another slide, which in the cyclonic mode has two counter-rotating gyres is a character of the circulation. This is after the 2007 shift in the AO, and then a larger Beaufort gyre that kind of fills the basin in the anticyclonic mode. Anyway, but the kind of cool thing, a thing that pops out of that is this thing that I kind of displayed as a worse yet. I think today, let's talk about it as a better yet, in which you see that the Beaufort gyre actually intensifies in terms of the gradient of dynamic height across the gyre. It actually increases, so we see with the EOF1, so that basically even while you're getting this cyclonic motion on the Russian side, you actually intensify the Beaufort gyre and collect more fresh water there. The connection also occurred to me that Sarah Dewey was trying to separate the ice edge linked salinity variations in the Beaufort Sea from the doming in the Beaufort Sea. So we could look at the salinity as the ice edge moved forward. And so she looked for various proxies or things to correlate with the doming of the Beaufort gyre. And actually the thing that worked the best, and this is over about 3 years, 2012 to 2014, was the AO lagged for 2 months. And so that's what that plot on the right shows, that there's a positive correlation between doming of the Beaufort gyre and the AO lagged 2 months, which is just another aspect of what we see in the EOF. I'm going to skip these for a later. I've stashed them here. Zip on to this. The transpolar drift, the question was how to define it and how it varies and the mixing across it. Well, I mean, my take on it is the transpolar drift's largely determined by the geostrophic velocity parallel to the transpolar front, and it's the front between Pacific and Atlantic derived water. And as for how to track it, we can use the zero vorticity line from ICESat, Cryosat, ICESat-2 dynamic ocean topography. Or we can kind of do it the old-fashioned way and make sections across the front. And this is a sequence of sections across the front, done basically along 90 west and 90 east. And if we look at it, we see that the core of the transpolar drift or in the ocean is kind of in the upper 200 meters or so of the water column. And what we found was that we tended to find the axis of the transpolar drift, basically across the pole, is shifted towards Canada when the AO is high, and then it spreads out and often kind of bifurcates when the AO is low. So in a sense, this is a way of tracking at least the impact of the AO on the transpolar drift. But it reflects that notion that when the AO is high, you're going to sort of squeeze the Beaufort gyre and shift the transpolar drift counterclockwise. A key question is how water properties are exchanged across the transpolar front and drift. And it seems like if we're only talking about geostrophic velocities, we aren't going to mix. And so it's going to be ageostrophic processes, eddies, and eddies were a huge discussion topic, I know, in our breakout session, and I think it was in several others. So eddies, and I think shelf type processes. Modes of variability of sea ice were a topic in at least one. I think there was an urge to revisit the Rigor et al. 2002 paper and maybe look at a different breakdown of time periods that included the more recent periods, last couple of decades. The effect of, and we don't know if this is a word, episodicity of temporal things and heterogeneity of spatial scales of forcing was a question, and how do these affect longer-term variability? For example, forcing by storms versus mean wind, or surface forcing by discontinuous ice cover with buoyancy flux and vero leads versus sort of an average, aerial average forcing. So that was another big issue. And I think that's about it. This is how I felt every day. So I think we should maybe, I think we've got time for what did we leave out? And the people that were at our breakout sessions, what did we leave out?
Yeah, so thanks, Jamie. I'm not going to say we left anything out, but we did have quite a detailed note from John Toole.
Yes.
And John, if you're online, we tried to synthesize it. We had a lot of discussions about it, but there are probably things in there that you might want to chime in on, John.
You think I can remember what I wrote the other day?
Yeah. Well,
my head is not full because everything drained out.
But for example, you talked about this idea that there's a different distribution of heat and salt, and does that ping any memory?
Sure.
Yeah.
So we had a brief discussion about how the fields that generate salinity anomalies are spatially and temporally different than the fields that generate temperature anomalies. Salinity is affected by river runoff and melt. That's largely surface inputs to the Arctic and tend to be kind of local to the Arctic, whereas all the heat that gets imported into the Arctic comes into the ocean from lower latitudes. And so it's rather a advective process, and these warm anomalies are often subsurface. And so the physical processes that redistribute surface waters and salinity anomalies may not be the same as the processes that redistribute heat anomalies around the basin. So yeah, there's sort of a disconnect that you can't think about them both in the same way. I guess that was a discussion point.
Yeah, I don't know, Mary Louise, I think we missed that part of it. Right.
No, we did get that part. I think, but
We
oh,
read that part,
Oh,
but I'm not sure we
absolutely. Yeah,
digested it.
we didn't translate it into one of the bullet points. Yeah.
I don't remember hearing too much about the overturning circulation in the Arctic. Is that something that we kind of missed a little bit, or did I just miss it? So with the water mass transformations and all that kind of stuff, and the transformation of surface waters into deep waters and Atlantic waters into deep and polar waters.
Yeah,
I certainly talked about it in my talk. You know, how it manifests in Asta. I don't know if it's real.
I think it's really, yeah. I'm saying yesterday, I don't think we picked that up. But if that was in John's thing,
John is saying he talked about it in his talk, in his Atlantic water
yeah,
talk.
absolutely.
Yes.
Yeah, so when we were synthesizing this, we were also talking about Atlantification and kind of regional differences of how things may change. And we have maybe more dense water formation now in kind of north of Svalbard, where we see that direct ventilation of Atlantic water compared to maybe more or increased stratification on the Pacific side of the Arctic. So we certainly talked about these regional differences, but again, they didn't really make it into this presentation here.
Mike, I see you have your hand up online.
Yeah, thanks. Sorry I couldn't make it in person today. I really like what John suggested about, the different processes for temperature and salinity because of the different sources. But I just have to slightly object because not all the heat in the Arctic comes from lower latitudes. I'm real focused on surface and SST, and so yeah, seasonally there's quite a lot of heat that gets into the Arctic Ocean locally, and
Sure.
And that's it's a huge part of the ice mass balance budget as well. So
yeah, sure.
Any more comments? Seeing none. Right? Okay. Yeah, we can move on to the second breakout group. Who's your elected speaker?
Hi, this is Effie Fine again. And we have just a couple slides, so if you are inspired to contribute more ideas to this, please feel free to interrupt me. Right, so we're talking about a couple of themes along this question about how can we use observational systems to understand a changing Arctic. We kind of followed the discussion questions we've been given and then added in like an extra bullet. So, oh, that didn't show up as well on the screen as it does in Google. But yeah, we had this nice map of the Arctic Ocean from Eddie Carmack. And the first thing we're talking about is the existing spatial and temporal gaps and biases in observations that we have. So many things came up, including there's a lack of observations on many of the shelf seas, including the Chukchi Shelf, the Greenland Shelf, especially some of these shelf seas along Russia. And there are a bunch of reasons for that. Some of these we think are kind of easier to remedy than others, where in some cases it might just be maybe we should write proposals to put more instruments in the Chukchi. In other cases, you know, there are economic exclusion zones, or later on we'll get into some of the difficulties with relationships with Russia. So that's kind of one point. Then we also talked a lot about sort of biases just in sampling systems. So one example was in the Eurasian coast, surface drifting buoys or ice tethered profilers that are deployed there get blown away by the winds that will come down off the continents. And so it's just harder to sample there. And there's a similar issue in a lot of the Eurasian basin where this warm inflow from the Atlantic enters. So both the deep basin and then the Bering Sea and the gateways into the Arctic there are just hard places to put drifting profilers because they'll tend to just drift through, and so we don't get the type of longer term nice conglomeration of floats that we get in the Beaufort Gyre. Another spot that was highlighted was the Markov Basin. I think this was one that we were feeling more optimistic that maybe we could just arrange to put more things there, because that shouldn't be as difficult, but you know, it's the northern edge of the Beaufort Gyre and then the exchange between the Canada and Markov basins that right now is undersampled, and it is logistically harder to deploy things up there, just in terms of getting a ship through a whole bunch of ice that even now is present in the summer. All right, and then, okay, so in general in the Arctic, yeah, the deep water masses are harder to sample. Most of our profiling systems have depth limits on them. And then very generally, all over the Arctic, ship and aircraft observations are constrained to mostly being in the summer seasons when the weather's at least most of the time okay. And even then, you know, if you're trying to fly a small aircraft in the Arctic, you're dealing with uncertainty about whether you'll be able to go out on a given day. And there are also a whole bunch of things that are just hard to measure. My text box got a little bit cut off here, but we had things like biogeochemical things are just, you know, you need specialized instruments. That's not always on a standard CTD. We talked about trace metals. We talked about turbulence, fluxes, including both oceanic fluxes that are related to turbulence measurements, but also fluxes between the air-sea, or the air and the ice, or the ice and the ocean. Those are all just hard things to measure. Air temperature, snow. I think we might have had one more thing, which I'm forgetting and just cut off on the slide. And then this led really naturally to a discussion of our wish list of all the things that maybe we could use to try and fill these gaps. So we could have, we're talking about if you could put biogeochemical sensors onto ITPs the same way that's been done with Argo, which has been really productive. We talked some about acoustic tomography, when I think one of our questions was maybe we should learn more about acoustic tomography and what's really required to do this well and what information we get from it. But this could be useful, especially where there's ice cover on both basin-wide and regional scales. We talked about gliders, which would need to be paired with navigational moorings to do observations under ice, but that's a way of getting into some of these boundary current areas where it's really hard to deploy drifters and have them stay there. We discussed the possibility of using Argo or deep Argo to get some of those deeper basin observations, and of course that's limited by ice cover, but it seems like they're getting to be maybe solutions to have Argo work with ice. We talked about sail drones, which we can drive around and make choices about where we sample, which also maybe are going to have CTDs on them at some point, which would be really cool. There have been some marine studies historically, and there also are maybe some modern submarine studies, and also we would like to have more submarine studies and use this as a platform. Unfortunately, a lot of the data that's exists already is classified, and we would totally love it if we could get some of it declassified and have access to studies that already exist that we just don't know about. We discussed bottom pressure sensors, which have some limitations, but also a lot of promise. We talked a little bit about drifter campaigns, and especially whether we're talking about these boundary currents that are difficult to put something in. But if we know where the inflow is happening and we have the opportunity to just put a whole bunch of drifters into a current, maybe that's exactly what we want, is to have things transiting through in some way that we sort of know the timescales of when we expect them to be there. The opportunities for Trans-Arctic cruise on the Healy in 2023. A really general comment was it would be great to have more sustained mooring, especially with the Nabus array maybe not having support with the Russian collaboration. That's a great way to have kind of long-term observations of a point. There are lots of opportunities with aircraft, both commercial and I forget what else. But we talked about aircraft. AXCTDs were another thing that were mentioned. Opportunities, so as tourism to the North Pole expands, that creates opportunities to maybe do some ride-along science. That also could be a possibility with shipping lanes opening up in the Arctic, for better or worse. Yeah, river influx data and tidal gauges. This kind of goes back to in some places there are political reasons that it's difficult to deploy those coastally, but there are also some places where that's not a problem and it's really just getting the access and deciding it's important to do it. And then a kind of broader comment was that it's great to have kind of mean observations, but the variability and statistics also matter a lot for the applications we've been discussing in terms of modeling and state estimates. And so just thinking about, do we need a single long-term measurement at one point, or is it good enough to say we're going to try and get some statistically accurate samplings of some region that gets us a handle on the variability, even if it doesn't tell us everything we'd like to know. And then the next thing we discussed was the kind of capabilities and the limitations of remote sensing and where we are with it and where it's going. So we currently have good estimates of sea ice motion over the entire Arctic. We have the sea surface height. We have ice characteristics like roughness and concentration. We're excited for SWOT to come online. We'll have good measurements of the geostrophic surface currents. We'll be eddy resolving at least in a good chunk of the Arctic. And ICESat-2 is providing this right now too. PACE will provide biogeochemical and SST data, which will be great. Sentinel gives gridded ice motion maps. And there'll be future satellites that sample the Arctic much more frequently, so we'll be getting like 3 samples a day starting in 2025 or 6. And then we talked about limitations of satellites. So I think we're familiar with these first couple ones, right? The sea ice makes it difficult to estimate wind and other parameters below sea ice. We can't measure air pressure, and we can get SSS and SST, but nothing beneath that surface. There are currently no plans for another SSS mission after SMOS and SMAP. And we don't have a great understanding about how thin ice impacts satellite-derived SSS and SST, so that's kind of an area for improvement. We talked a little bit about separating steric and non-steric SSH, and that's a very difficult problem. And then we also discussed, it's totally great to have SWOT and these new high-resolution observations, but that actually makes there be a need for tidal models on really high resolution scales, on shelves and in the fjords, because we'll have data on those scales, but we'll be able to do more with it if we can, remove the tide and look at sea level rise and things like this. And similarly, geoids exist, but they need improvement for these really high resolution applications. We talked a little bit about blending of in situ and remote sensing data, and part of that discussion was about whether that's a good idea and different ways to do this. And we're saying optimal interpolation might be, numerically give you the best correlations to observations, but then with numerical models, you actually get a picture of the ocean that's dynamically consistent, so trade-offs both ways. Blending data introduces errors, and we think sometimes the original observations might actually be more useful. And particularly the data assimilation is making assumptions about length and time scales. So those assumptions need to be treated with care. And then also with the final product, it can be kind of deceptive to have just a map that looks really nice, because in some places that map,
has recent data that was assimilated. In other places, maybe it's kind of just reverting to a model because there wasn't very much data to assimilate. And then if we're comparing data assimilation products with data, you really want to know if the data was assimilated or not. And so just making all of that really clear for these products is helpful. We kind of talked a bit about that there are rules for data assimilation and high resolution modeling for things aside from like these sort of state estimates where we're just trying to make a data product. We can use them to leverage sparse observations and understand what we're really getting out of them. We can think about using these in ways that would help determine optimal observational sampling or provide situational awareness when people are designing a mooring array or thinking about where to go on a process cruise. So there's a lot of usefulness for these things, even beyond like a kind of general state estimate. Talked a little bit about if there are ways to, some of these things we've been discussing kind of give you like one data point. So we have like the bottom pressure, but if you could co-locate bottom pressure and acoustic tomography and put those on a satellite track, so we have local SSH and SSS, then you can kind of take these point measurements and maybe get something more than you would be able to get from any single one of them, because the bottom pressure is more useful if you have some information about the content of the water column and the density of the surface. So maybe there are ways to think about designing a system that would let you make these sort of point-wise, low-budget measurements in a way that gives you optimal information out of them. And similarly, there are new sea surface height buoys that have really accurate measurements of sea surface height, and so using those in ways that also co-locate with the satellite measurements allows for better confidence in the sort of regional SSH. And then our final bullet point was how are we going to overcome the degradation of relations with Russia? So this is a really big question. And we kind of just brainstormed some ideas. So one is that we really would like to leverage icebreakers from other countries to plan or extend cruises into the Eurasian Arctic. And there are a number of groups that are invested in these kinds of long-term observational plans, including the Arctic Icebreaker Coordinating Committee, the Pacific Arctic Group, IARPC, and so just being really clear that this is a need and it's going to be a problem going forwards might help keep some of these programs running. So SciSex, I guess, was the naval program to release data from submarines. And so is there any chance of reviving something like that that would give us more accurate to measurement, more access to measurements and opportunities to deploy instruments? We're kind of by necessity going to be relying more on models and satellites to fill gaps on the Russian side. And as part of that, maybe we also want to think about the autonomous vehicles that have the ability to be steered into gaps, so that in some of these places where it's hard to collect data, we have the ability to force our instruments to do that. So like gliders, floats, and sail drones might be useful for those kinds of applications. Or this kind of idea about if we care about ocean currents and we want to sample them, maybe we want to deploy things like Argo floats directly into the currents instead of into ice, so that we're really sampling the long flow pathways. And then our final point was just that multinational collaboration can potentially be helpful in using data gaps resulting from the US and Russia relations. So an example that came up in my discussion group was like there are observations by Chinese and Korean researchers on the western side of the Bering Strait, and that data was published in US journals, and so now it's actually available. These are, I think, nutrient measurements. And so this is kind of an example of if we can develop multinational collaboration, then we're not quite so reliant on a relationship that might be tense right now. Yeah, so if anyone wants to contribute more ideas, that would be great.
We have time for a couple of questions or comments. Anybody has any?
Can I make thanks, Effie. That was an awesome summary. This is a question for maybe Jamie and maybe others. What is the current state of springtime operations from aircraft?
Right. Well, I think it should still be feasible of certain kinds. What we used to do with the NPO project was fly a ski-equipped Twin Otter and land on the ice, and depended on the pilots, but commonly most of the pilots like to land on refrozen leads because they're smooth. And so it was, the challenge was to figure out what's refrozen enough to land and still be smooth. But there were a few guys that really had a good eye for that. There was, and I think that's still possible. As a matter of fact, at the beginning of NPO in 2000 or so, you know, you had to search for the refrozen leads. By the end in 2015, pretty much a lot of the ice was refrozen leads. It was sort of just a matter of picking which ones were thick enough. And then we could land, drill a hole, and put down a CTD. I don't know. I was going to address something with my stashed away slides, and then sorry. Can we find my breakout one? Oh, okay. I see. Yeah. You mentioned kind of a bunch of things that I thought I should clarify something. And that's the use of GRACE bottom pressure measurements and satellite dynamic ocean topography, and comparing those with in situ observations. And the in situ observations are just repeat CTD stations. So this is a plot of trends from 2005 to 2008 of IceSat DOT. Those are the color contours. And then those triangles are GRACE bottom pressure minus CTD steric pressure triangle. So, I mean, I think the issue is raised, how do you separate the steric component from the total mass change? Well, that's what this is, set up so that basically we're getting a dynamic height trend and then adjusted for bottom pressure to make it more equivalent to dynamic ocean topography. So that's what those triangles are. And you can see we got a pretty good agreement. I mean, well, there are a lot of triangles there, especially around the North Pole, this 90 west, 90 east section, where it's pretty hard to see the green triangles because they match the color contours. And then if you think through that, you say, well, okay, if GRACE and dynamic topography agree with hydrography, you start to think, well, does that mean that the freshwater content agrees with the difference between GRACE and dynamic ocean topography from the satellite? And that gives us, that can be correlated with the total freshwater content. So you're basically measuring the average density of the water column. When you measure a change in GRACE and a change in DOT, you can get a change in average density or freshwater content. And so here we've kind of torqued it around. So one scale that in black is what we call the steric pressure, and then we used a correlation minus 0.36 times that, and that gives you the freshwater content. And the thing about this is, I think it works. The freshwater content we got for the deep basin overall the change was pretty small. There's a huge increase in freshwater content during this period in the Beaufort, but meanwhile, because of this cyclonic mode, it mostly was fresh water that was lost from the Russian side of the Arctic. And it came out with a balance that agreed pretty well with the hydrography derived result of Rob et al. In 2011. And then when we went beyond the deep basin and included the whole area, basically it was a very small, almost negligible total freshwater content change. So anyway, I think the technique is valuable, and of course, it gets you into the areas that you can't make a CTD measurement in, especially now. Anyway, I just wanted to make sure that was clear.
I'm sorry, we have to go on for the next one, but we're going to have some time for more discussion later on after the third report. So whoever has been subjected, Marion, okay. Voluntold, yep.
Okay, so gonna do my best. We had a lot, and I'm gonna give a recap kind of question by question. So we started talking about the gaps in high latitude modeling, and these could kind of cover a wide range of things. So specific to gaps related to modeling, the things that came up, or kind of the top one was parameterizations, and specifically verifying or evaluating the quality and the applicability of our existing parameterizations for things like vertical mixing, eddies, and kind of, I guess, general like convective small scale parameterizations for high latitudes in the Arctic environment. In addition, we had a lot of discussion about gaps in our understanding about how to appropriately model the physics related to coupling between specifically the shelf and the basins. So how are those exchanges represented currently in our model, and how do we kind of merge our understanding from observational studies and process scale simulations to meet the needs of these kind of global and regional scale simulations. Also air-sea ice exchanges and fluxes, that was another kind of gap in our understanding of how we're simulating these things relative to what we understand from more process-based studies. And that kind of highlights what was this recurring theme, was this scientific knowledge transfer gap. So we noted that, you know, one of the parameterizations we were thinking, or we highlighted as being kind of a gap, this eddy parameterization, so how eddies transport tracers across basin, and also the influence that they have on the energy cascade. There's a whole CPT devoted to this topic right now. And we recognize that there are individuals from the Arctic community that are involved in this process, but given the, you know, Rossby radius of the Arctic and the, you know, current simulation, or the current resolution of simulation and Moore's law, and how fast we're going to start approaching being able to explicitly resolve eddies in our simulations, we felt that, you know, this CPT has a huge potential value for the Arctic community. And we really highlighted the, you know, at present, there's not a clear, or we didn't feel like there was a clear connection being made between the Arctic community and this particular CTP. And so this was like a gap that we felt could be really valuable for us to go and try to remedy. So to make sure what comes out of this CPT is really relevant to the region that's going to be the last place where we can explicitly resolve eddies in any of our global climate models. And yeah, how do we get their ear, and how do we get us all in a room and talking? In terms of the gaps for modeling and for observations, I think from a modeling perspective, we come and we see all the observational work that's been done, and it's fantastic, but how do you merge it all into a product that's really meaningful and useful for comparison and an evaluation of models? And also a need to identify kind of what are the key metrics for both the observational community and the modeling community for us to, one, fully understand what's happening in the Arctic, and then evaluate how well our simulations are capturing those physical processes. And so we really identified this gap where, you know, there was a need for us to be, both these communities to be coming together and kind of identifying these key metrics, and then figuring out how do we consistently evaluate those in our simulations. And then we tried to come up with a few of these key metrics. So gateway transports, definitions of Atlantic and Pacific waters, EOFs of sea surface height variability, but we really felt that this was a topic on its own that deserved kind of a collaborative effort. And And then also a thing that we felt was kind of fit into this category as a gap was support of model development, observational availability, and knowledge transfer. So support by funding agencies, but also support by the general kind of ways in which people are evaluated, or specifically early career folks. Like, you know, it's not particularly, what's the word I'm looking for? Beneficial for your career as an early career person to put a lot of time into model evaluation, because you can't get, you know, these nice high impact papers, which is how you get a real job. And so we're often dissuaded from putting too much time and effort into things which have huge long-term benefits for community and even for our own personal science, if we can be given an opportunity to take this long-term perspective. And so this was kind of this gap which we feel sits here, where we want to be able to do this very important work, but we're currently not incentivized to do that in a way which actually would benefit our scientific community in a long-term, very meaningful way. So just this gap in incentives and how we're kind of being led to do our science. And so that could be, you know, that could come out of, or changes could be made from kind of the funding agency side, where we thought there's potentially a space for that. Okay, so the good things, what are we excited about? What are the modeling capabilities that really have come forward in the last years and helped us? And so resolution, that was a really big one that came up, I think, in every single group. The idea of using these unstructured grids to really, you know, pile on the resolution in a region like the Arctic, and try to start getting at some of the processes that we felt like there were a lot of uncertainties in the first slide that I mentioned. The sea ice parameterization, so what Liz showed yesterday with the land-fast ice parameterizations, and then what other groups have shown with rafting and ridging, you know, these are really nice improvements in our parameterizations that have led us to better simulate the sea ice in the Arctic. And then somebody also brought up this emergence of these offline tracer models. So you can run passive tracers through your simulations offline. It's computationally really efficient, and you can learn so much. So just the emergence of these particular methods we felt were, you know, really great achievements and things that should help us move forward in building our understanding. So observational gaps that hamper the production of useful Arctic reanalysis or model initialization efforts. So I think Effie covered a ton of observational gaps, and I think, you know, from a modeling perspective, we would agree, but there were a couple really key things, or there was one key variable that was brought up, and so that was the sea level pressure, and this was, I think, highlighted in one of the talks yesterday, where the sensitivity of the Arctic circulation to the way sea level pressure is, or the forcing related to sea level pressure, that was really highlighted as, you know, something that the Arctic is really sensitive to, and we have some key observational gaps. And so also trying to leverage, and this was also brought up, these, the data assimilation simulations, which were also mentioned, to understand, like, given our limited resources and, you know, challenges of getting observations of sea level pressure, how do we identify these key regions and make the most of our limited resources? And then I think the other kind of gap in the observations was a platform. And so actually we were all complaining about this, and then we Googled and we found out there is actually the Arctic Data Center, which is run by the National Science Foundation. And so maybe it's not really that we're missing a platform, but we're really missing to get that information out to the community and have everybody, you know, using it efficiently and, you know, raising its profile. And also getting things, getting these, you know, important state or variables put on similar grids or in a very useful format. So maybe we have the platform, but maybe we need to be thinking about how do we have this platform better serve the needs of its users. Okay. Oh, right. Is this still extinct? Also, making better use of the data that we already have. So Liz, this is a figure from Liz, and the two maps are on the left is the altimetry data that's available for their simulations, and then on the right is the blue little dots are the altimetry that's actually assimilated into the simulations. And so you can see we have all this data and it's not being appropriately used. So improving the way that or changing our methods for assimilating data so that we're using more of what's already available. So being more efficient or making better use of what we have. That was another kind of key area that the modeling community could make improvements on. Okay, so coordinated modeling studies. And we interpreted this a little bit more liberally and saw coordinated modeling and observational studies. And so to come back to the one that I brought up at the first slide, shelf processes, I think there was across a few groups were identified as a gap in our scientific knowledge, and particularly for the modeling community. And first, we really felt like we needed to there needs to be some kind of synthesis, so a review paper where we're taking the existing, theory, observations, and modeling studies and synthesizing them into kind of a coherent picture of what we do know and what we don't know, so we can identify where we do have gaps in our understanding of these shelf processes, particularly gaps that inhibit us from appropriately simulating these processes in our larger scale models. And then using that to kind of guide what are the key questions there, and what can we do to address those questions. And then, right, this was one that had a bunch of sub-questions about like multi-model versus single model, which is better. And we thought this is not a good question. They're both good, and it just depends on what you're interested in looking at. So we felt, all of the tools that are identified in these sub-questions are useful, and it's just adjusting them for the problem that you're considering. And then we came up against this again and again is, maybe we need to really be offering the, global modeling community a metric or a scorecard that's specifically for the Arctic. So a unified set of metrics that modeling centers around the world can evaluate relatively straightforwardly and easily, and get a scorecard that's a holistic understanding of, okay, you're getting the sea ice extent right, but are you getting it right for the right reasons? Or is your ocean below, completely unphysical? And so, giving people an insight into whether they're getting the physics of the Arctic correct in their simulations. And so we liked this workshop so much, we thought, why don't we do another one? One where we can get together and have the modeling and the observational community come together and decide, what are these key metrics? How do we simulate them? Do we have, very clear observational evidence to indicate what the values for these metrics should be? And if we don't, what needs to happen to, sustain our observational networks or build out our observational networks, so we can constantly monitor these metrics also, so we can understand how these metrics are going to change in a forced climate scenario. And there was a suggestion for an Arctic Ocean MIP as well. And I think that was it. Oh, right. This was a key point that was raised. Somebody wanted to make sure that, we noted that communication between the observationalists and the modelists was really improved. And this is really great, and we should be pleased with it, and we should keep doing it and work very hard to maintain that. So, yeah, I'll leave it here. And please, somebody else fill in if I missed something.
Any comments or points to add, or?
There was a hand up on the virtual too.
Yeah, put it down.
Sorry, Marion, this is a really simple question, but what's a MIP?
Model intercomparison project.
Thank you.
Yep. Mike in the back.
Yeah, and can you elaborate a little more about what the motivation for an Atlantic Ocean MIP would be, and why would we need one?
Like an Arctic Ocean MIP?
I'm sorry, Arctic Ocean MIP.
Yeah, I think this is coming out of a few recent papers which are showing pretty consistently across CMIP6 models that representation of the Arctic ocean is kind of a key issue for many models. And I think also we saw that kind of yesterday in these talks where, we're missing key features like the Pacific summer water in these models, and that's a huge source of heat and presents a lot of uncertainty in our ability to predict, sea ice on climate scales, because we're kind of missing a key source of heat below the halocline. Right. So I think it really came out of seeing the talks from yesterday and a few of these other papers kind of highlighting what are these consistent issues across CMIP 6 models.
Patrick, I see you have your hand up.
Thanks for a really great summary and list of ideas with regards to the Arctic MIP. Just one sort of cautionary note, that's something that needs to be carefully considered. The OMIP effort, the Ocean Model Intercomparison Project, spent many years of trying to define a common forcing data set, right? And so that consisted in, over the years, basically developing the core forcings, but also along with the core forcing, a set of bulk formula that were implemented across all of the ocean models, so that you have both the same atmospheric forcing and in the same way to convert this to air sea heat fluxes. And if you don't care about sea ice, you could say, well, the sea ice model is just a sophisticated bulk formula. And especially for the AMOC portion of the OMIP analysis, several papers like by Gökhan, Danabasolu published too, the AMOC was very diverse, very spread out, unlike other comparisons. And I think really the main issue here is that the minute you bring in sea ice, of course, the whole concept of having the same forcing is out the window, because the bulk formula, the sea ice model, that is becomes very different. And so in formulating an Arctic OMIP or MIP, one has to very carefully consider how to disentangle ocean circulation aspects to coupling. I just saw so you didn't understand anything that I was saying?
No, we heard you.
We could hear
Yeah,
you.
Okay,
actually.
I was told. Okay, so anyway, so that is that the sea ice portion as the coupler between those two components, and the fact that there are both the models, the ocean models are different and the sea ice models, could make this, at least some thought has to be placed into that.
Patrick, since I have you, so I appreciate your concerns and kind of the key issues you want us to be aware of for the MIPS. What about the other kind of proposed suggestion that we have with the, like a key set of metrics, basically like an Arctic Ocean report card?
I think that would be great, and it would be great to develop those metrics across the different communities. So the ocean community, the CMIP community, they usually have their metrics. Potentially also the reanalysis community. Oftentimes they are decoupled, and having sort of something that can be agreed upon across those at least 3 different communities. So I think that would be really valuable to have a sort of a discussion on this. There is, I think, ongoing for the AMOC, there is, for example, again, Gökhan Danabasolu, he is leading an effort on developing metrics for AMOC-related topics, and maybe one can learn from there. And then I also really loved your suggestion about connecting to the CPT eddy parameterizations. And I think because I think the role of eddies in the Arctic is still the undervalued parts, because it's still sort of maybe beyond reach or so. And I also really like that suggestion.
Thank you.
Mike, I see you have your hand up.
Yeah, with regard to MIP, Model Intercomparison Project, so I think Andre Proshtinsky is on here as well, but so Andre and I were involved with AOMIP for a number of years, and we changed the name to FAMOUS, and the F is Forum, because we tried to do a MIP and it was a spectacular failure. The sea ice is a very sensitive parameter. And so if you tell a bunch of modelers, here is your atmospheric forcing, here's the albedo you should use, all of these things, some modelers will get sea ice that's 50 meters thick, and some will get no sea ice. And this is true even if, you know, just the watts per meter squared are just slightly different, you know? I mean, it's just, sea ice is so sensitive. So, you know, you can try to run a map, but it's a tricky thing is all I'm gonna say. And now I wanna just say something else. Marion, you had in one of your first slides, you said something that got me very depressed, which was the Arctic will be the last place that eddies are resolved or the mesoscale is resolved in the world. But then your very next slide, you talked about resolution, about unstructured grids. You didn't mention it, but you know, there's the tripolar grids that in fact even, you know, have higher resolution up in the Arctic. So I'm not so sure that it's so, you know, bad really. I mean, yes, the eddies are, everything is very small scale up in the Arctic, but there are reasons to believe that the resolution might be the best in the Arctic as well. So maybe it's not so bad.
Yeah, totally agree. I think we have, you know, things working against us, things working for us. I think the key point was that, you know, resolution solving all of our eddy problems everywhere on the globe is still a couple decades off with Moore's law. And we have to solve climate like problems before then. And so we still have to use, you can't throw up, you know, put all your hope on resolution and ignore parameterizations, I think was we have to understand this balance and how do we work with it.
Seeing a thumb up from Patrick, and we have to move on, but I want to give a final comment to Wilbert.
Yeah, in terms of the Arctic Ocean Model and Comparison Project, one thing that could be envisioned is to do something like the sea ice model intercomparison project, sea ice MIP, which was purely a diagnostic MIP. So basically, they requested additional variables that are not part of the standard output of the regular MIPs, basically. So rather than proposing a specific experimental protocol, for instance, we can say, okay, Arctic Ocean Model Intercomparison Project would be requesting additional variables, maybe a transport through certain gateways, which is not part of the regular set of metrics, for instance. And I'm pretty sure this community can come up with additional things that are important for us, but that cannot be extracted from the regular model output.
All right, and with that, we'll move on to our next agenda item, but I'd like to say thank you again to Marion, Effie, and Jamie. Yeah, Jamie pulled the rug out under for me on this one, so I don't know what we're doing right now.
Well, I think this was time that was scheduled for agency input, but I don't think we have any funding agencies here. And so we've got another thought, and this is kind of coming from Mike and Patterson and I. I mentioned when we started off that I held up the example of understanding ENSO, the toga, tau array, the whole development of that, and what a fine example it was of a group of scientists getting together and realizing there was a common problem area or an issue, a question that needed answering, and it was going to take observations and modeling and then a lot of analysis that was coordinated towards in that case, a science question. What makes El Nino occur, and how can we predict it? And out of that grew a kind of a coordinated, concentrated effort that was very successful. And what I'm thinking, and I really loved about the last two, well, the last two comments are gone now, but the last two or three thoughts of the modeling discussion, because they talked about getting together, having another workshop. In other words, it told me that the modeling groups were looking at this and saying, gee, this is fruitful to get together with observationalists and analysts and to talk about what we're seeing. And so what I'm asking, I guess, is who's interested? I mean, if we want to do this kind of coordinated modeling, observing effort, and we want to get some funding to do it and some cooperation to get out into these hard to access areas, to develop appropriate techniques for doing that and appropriate new observing tools. We're going to need to get some funding to support that. And I think this workshop is perfectly designed to sort of plant the seed to grow an effort that the next phase of such an effort would be for people to get together and figure out some key science questions, things that, well, I think somebody was talking about metrics. The other way to look at it, kind of from the overarching perspective, is what's the science question? And I think here at the end, it was mentioned that in this discussion of MIPS, that one rationale was in the larger scale models, I think somebody said mega models, the Arctic was standing out as the poor relation that was not kind of understood well enough or modeled well enough. It seems like that's a golden kind of motivation for having a real effort to do a better job of understanding the changes in Arctic Ocean circulation and ice cover and the kinds of things that we've been talking about. So I guess the question is, how many of you are interested in working some more on trying to kind of refine our questions and our issues and putting together an effort where we're eventually proposing to the agencies. We've got 4 or 5 agencies here that have shown enough interest in this to put funding into this workshop. So it's not like we're starting from zero. I think the mood should be increasingly receptive to hot ideas that are really well presented and encompass a large range of scientific disciplines. I mean, if we have the modelers and the observationalists and the people that analyze both of those kind of getting together and saying, this is a big question that we need to address, I think it could carry a lot of weight. So that's kind of all I can say. Really, I'm just interested in what you all think about doing something like that. I don't see any hands going up. There we go. Thank you.
Yeah, I don't really want to hog this meeting, but I think it's one thing that I want to mention is that so I'm part of the Highlight Resin project, and we're in our kind of a renewal process. For the next phase, we're proposing to do a community effort that we're referring to as CAMAS, the Consortium for the Advancement of Marine Arctic System Science, which would be kind of more or less modeled after FAMOS in terms of organizing some annual workshops, basically, where some of these ideas can be can be put into practice, basically. It would be a forum for people to get together, define these research questions, define some way to address them, maybe through a couple coordinated experiments or maybe metrics development, and that can then be executed in the matter of a couple of years. So it's pending whether our project reviews well and gets funded. But I just thought I'd throw this out. It would have support from DOE and ONR has also shown interest in supporting that. And Mike Steele is part of this effort also. CAMASS, CAMASS.
Anybody else? Oh, Mike?
Yeah.
Go first.
Okay, thanks. So as Wilbert says, yeah, we're hoping to sort of restart that forum. That forum was it's based more on the modeling, though certainly interacting with observationalists. I think Jamie is proposing something slightly different, and you can tell me if I'm wrong, Jamie. But I mean, I think Jamie is proposing something more along the lines of imagining a new Arctic observing system, or maybe, if not system, not long term, maybe even shorter term. Like, how are we going to address some pressing observational issues of the day? And I think that's not quite the same thing as what Wilbert was talking about, and I think that has value as well.
Jamie, do you want to reply to that? Okay. 1 second, Patrick.
Well, yeah, you're both right. I don't know. I might try and call it the Arctic Understanding Network. I think the key is that I wouldn't want to favor modeling over observations. I kind of want to get at the questions and kind of do the crime scene investigator approach, and bring all the tools together and use them in a really coordinated way. And I mean, especially we have an area, more than half the Arctic Ocean we can hardly get to. But we do have some indications of, for example, correlations between things that happen in the areas we can measure and things that happen in areas where we can't measure in situ, but maybe measure in remote sensing. And it seems to me these data modeling and data assimilation techniques are the magic way to put together a comprehensive picture over both the areas we can make in situ observations and the other areas. So I'd like to see Mike sort of suggested had the tone of observing, and Wilbert had more the tone of modeling intercomparison. And I think if we put those together and come up with some compelling issues that the agencies will have to fund, we can get the kinds of things that we need to really make progress understanding the circulation of the ocean. I've talked too much.
Patrick?
It's full.
No, I only wanted to briefly bring in another aspect, which is the international portion. It's really a shame that the Arctic Passion, which is sort of a recent, larger funded EU effort, that they had their workshop exactly at the same time as ours. But I think despite that, I think it would be good to. It seems to be, or what's the EU Polar Net or something, but I think they're really one of the main drivers now in Europe, and the famous people at least know one of their leads, Michael Karcher, very well, and it could be Wilbert, in your effort to see whether there could be even, there could be sort of buy-in, at least in ideal terms from that community as well. Just a comment. Yeah.
Anyone want to add anything here? Oh, Sylvia, so you have your hand up.
Yeah, I'll just add in 2 cents that it seems like there is no shortage of issues in the Arctic that could require a big effort like this. And it's more the consensus around identifying an issue that's going to be a hard part in some ways. There's even small questions that could require a big effort to figure out how sea ice mediates the process or anything like that.
So Sylvia, you're a part of the CPT on eddy mixing, right? Can you talk a little bit about your if there's any interest or activities geared towards the Arctic?
Yeah, so I'm involved in the eddy energy CPT from the observational perspective. And I guess what I would say is that, the CPT can't do everything. So they're focusing on not ice covered regions with the expectation that whatever improvement you make in the rest of the ocean is also going to help improve the representation of the ocean under sea ice. And to that, I would say yes, but also that there are some unique aspects of, say, eddies and sea ice, and maybe how sea ice dissipates the eddies that are specific to the higher latitudes and the under ice that simply aren't getting tackled. And so you would honestly need a specific sort of high latitude focused effort to address some of these issues. But certainly, getting people in the room and talking is doable and should help in some sense.
All right, here radio silence. So maybe do you want to wrap this up?
Yeah, I guess so. So, Sylvia, given that, let me ask a simple question. If we had another workshop 6 months or say, would you be interested in coming?
Yes, I'm certainly interested in figuring this mess out.
Okay, okay. Okay, well, we really appreciate everybody coming to this workshop. It was a long time in coming with all the postponements and so forth, and we certainly appreciate you all taking the time out of your busy schedules to come. I'd especially like to thank the session leads who stepped up and ran the sessions and the note takers in the breakouts sessions. I know for our category, the note takers were vital in reminding us of all the different things that were brought up. I'd like to thank the organizing committee, Dimitri, Patrick, Allison, and Mary Louise. They also sat through numerous Zoom meetings, and they were a big part of my Zoom world, and an important one. And I think they really entered into the whole thing in a spirited way that was really well. It wouldn't have happened without their work on the project. And of course, I want to thank the sponsoring agencies that included 2 ONR programs, both the physical oceanography and the Arctic programs, NASA physical oceanography, and was a big part of this. And as a matter of fact, in some ways, the input of Eric Lundquist was kind of crucial. And I think it now, whereas before we didn't look to physical oceanography at NASA or Arctic sort of work, in the current, kind of beginning with the development of this workshop, I think physical oceanography now will take an interest in supporting work in the Arctic. NOAA Climate and Variability and Prediction and the Modeling, Analysis, and Predictions projects are important in the workshop. And also, I think it's long been the sentiment that a lot of a big need in the Arctic is for basically ongoing measurements. And that kind of gets, there's a polite way of saying that is ongoing measurements, and then people will kind of revert to monitoring. But whatever that is, when it comes up to monitoring, then a lot of the other agencies tend to think of this as, well, that's NOAA's job. And I think NOAA would be willing to do more of that, but they need us to say, we really need to have continuous measurements. We need an Arctic toga tau array to keep going. And so I think, the potential for their contribution to a program to get the kind of measurements that we want could be huge. And then I'd like to thank NSF Physical Oceanography and the Arctic Natural Sciences Program. They have, of course, NSF with their AON program and search leadership has been instrumental in the observations that we've gotten to make in the last 20 years. And so we can thank them for not only the workshop, but a lot of the data that you've seen discussed. And finally, I'd like to thank the Clivar office, Sam Colloquy and Jenny Zhu and Cindy Grady, and especially Mike Patterson. Mike has had a real clear understanding of how to do this kind of thing, and kind of what kind of organization and what kind of workshops produce, well, the seeds of ongoing sort of efforts. And so really appreciate his experience and understanding. And I'd like to thank especially Sam Colloquy. He's really a great master of ceremonies. And I mean, I'm not good at keeping on the schedule anyway. And then if I want to concentrate on the science, I just completely lose track. And so I think we'd be in big trouble. It would be, late this afternoon before we were here at this point if we hadn't had Sam. And I'd like to thank Lucas Demaria. He really stepped in with all the IT stuff. And I'm not going to go into the details of how difficult what we were dealing with, trying to figure out what to do with everybody coming out of COVID. And he just kind of took over. And when I showed up the first hour and Lucas was here with a sea of it looked like he was going on an oceanographic cruise. He had cables and equipments and Arctic boxes everywhere. And I was thinking, okay, we got the right guy. And he's just proven that. So thanks a lot, Lucas. Okay. And mostly, I'd like to thank all of you for coming and providing what, for me, was a really stimulating and exciting discussion, 4 days of discussion. So thank you very much.
Okay, we're going to be getting started here with the breakout reports soon.